Now we've been saying that things start to be different when they become digital. And so let's talk about what's involved in making a sound digital, digitizing a sound. What we're talking about today is called the sampling theorem, and it's named for Harry Nyquist and Claude Shannon. Now remember we said sound is produced either by a speaker or something like it that's shaking the air like a speaker does. And if we're recording it, we're picking it up with a microphone, which works like a speaker backwards. It has a membrane just like our ears do, and it moves back and forth in response to the sound waves, pushing a coil in proximity to a magnet that makes electrons fluctuate on that coil of wire in the shape analogous to the sound waves. That's how we get our sound into an analog electrical signal. To digitize it, to turn it into digits, we use an audio interface. And so we plug our microphone into a box like one of these, and it measures the amplitude of the electrical signal coming in. So it's easy enough to imagine an electrical signal coming in that's fluctuating in voltage. And at any given point, we can measure that voltage. And so we can keep measuring it as it changes, measure, measure, measure. And each of these measurements we call one sample, as in a data sample, just like in science experiments. If you're playing country music and rock music for a plant and you're measuring every day how tall it is, you're taking a data sample. But how often we sample our wave matters. We call that the sampling rate. If I don't measure the amplitude of my wave frequently enough, connecting the dot gives us the wrong impression. We end up with something that might be going in the wrong direction and much too slowly. This is a wave that has the wrong frequency, and so it's an imposter. We call it an alias, or we call this effect aliasing. So the rule of the Nyquist-Shannon sampling theorem is that we need to be sampling fast enough to catch a wave once above zero and once below zero. That means it needs to be going twice as fast as the highest frequency we need to capture. Put the other way, given a sampling rate, say 48,000 times per second, we would only be able to faithfully represent a sound that's half of that. This has to be double the highest frequency that we want to represent. And so the Nyquist frequency is half of our sampling rate, and that represents the highest frequency that we can represent faithfully. Any frequency over the Nyquist frequency gets misrepresented as an alias. Let's see what that's like. We're going to simulate that by lowering our sampling rate. And here I'm going to introduce our frequency domain view of sound. So far, we've only been looking at a time domain representation of sound, where we can see how the amplitude changes over time. Maybe you remember in math class when we talked about not just the x-axis and the y-axis, but the domain and the range. The domain is the x-axis, but time is on the domain. So we can do some math called a Fourier transform and look at a sound and break it into sine waves so that we get frequency along the domain, and amplitude is still on our vertical axis here. And so we get one spike every place there's one sine wave in our sound. So far we're just playing sine waves, so we'll see one spike. So let's see what happens when we raise our sound up above the Nyquist frequency, half the sampling rate. I'm going to leave our sound down for this. So our wave is going to increase in frequency, means its period shrinks. And here we can see the spike increasing in frequency, moving from left to right, all the way up toward the point that reaches half of our sampling rate. Our sampling rate is 48,000 hertz. So half of that sampling rate would be 24,000 hertz. So watch what happens when we get up toward the top end of this graph here. It goes up and up and up. Once it reaches 24,000 hertz, remember we saw all these funny artifacts visually in our time domain view? Well, watch what happens when we pass the Nyquist frequency in our frequency domain view. I'm still going up in frequency. See, check my frequency, I'm going up. But we see our spike going down. We're getting a false reading because we're not sampling our wave fast enough to capture it accurately. That's what we just saw in our graph. If we weren't sampling our frequency accurately enough, we would get something that was too low. A false frequency, an alias. This is aliasing. And the higher we go up, the more it goes down until it reaches zero. And look, I'll keep raising my frequency. Now I'm at the sample rate and going above it. It's never going to go negative. It bounces off 0 and goes back up. This phenomenon where values that go out of bounds get folded back in bounds between 0 and the Nyquist frequency, half the sampling rate, this effect is called foldover. And so foldover is synonymous with aliasing, which means our sample rate isn't high enough or our frequencies are too high to be captured faithfully by the sample rate. What does it sound like? Okay, let's simulate it by listening to our 100 hertz tone. I'll fade it in. Now let's lower the sampling rate. Here we're at 28,000 hertz. Let's only sample it at 24,000 hertz. Sounds the same. And half again. 12,000 hertz. But look, we can start to see we're losing resolution. Not vertical resolution, horizontal resolution along the time axis. Cut it in half again. 6,000 hertz. We're losing some resolution. Cut it in half again. Oh, now we hear some artifacts. And look, we can see it too. Some other humps happening in here. Okay, that's annoying, so let's cut it in half again. I'll turn it down a little bit. Okay, much lower resolution here. We can cut it in half again. Even worse artifacts. We can still see when it goes up and goes down, so we're still capturing that. We can still tell what main pitch is being played, but we're getting some other not so pure artifacts in here. Now watch as I go down in sampling rate more. You can still hear that bass frequency. Ooh, ooh, but this other stuff gets in the way. And notice some of them are moving up. Some of them keep moving up so far that they fold over, and so we see some of them moving up and others moving down. Some of them move down so far that they fold back over, and we see more moving up. And so we can see them not being so, we see multiple humps, and we see them not being so symmetrical. And we see a really crummy, low-resolution version of our wave here. Now the tone we're listening at is at the Nyquist frequency, as our sampling rate is 200 hertz, and we're playing the Nyquist frequency at 100 hertz. If our sampling rate goes any lower than that, this tone is going to be over the Nyquist frequency, and it's going to be misinterpreted, so even the main identity of this pitch is going to be lost. And game over, right? Okay, let's restore our sampling rate back up high again. Notice these artifacts moving back and forth because of the foldover. And getting smaller and smaller, our resolution comes back. You can hear some high parts moving up and parts moving down because of that foldover. These are all aliases or aliasing effect. Now that's our horizontal resolution, and that's what happens when it gets bad. What about our vertical resolution? This is how we're measuring the amplitude at each sample. Amplitude is the loudness, and since we're digitizing it, we're measuring it in terms of digits. Our resolution consists of how many digits we're using to represent that sound. Now, because of the engineering involved, we've built a machine that converts a voltage into numbers somehow. It's convenient to use binary numbers. And so when we're talking about digits, we're not talking about digits 0 through 9, but just 0 and 1, binary digits or bits. And so if we could only use one bit to represent our signal, even if we're measuring it 48,000 times per second, we're still only going to be able to have two values. Now, it looks like we have an in-between value here as an artifact of the visualization, but really we've got two values, 0 or 1, all the way down or all the way up. Is it low or is it high? and it looks not like a sine wave, but like a edgy square wave. This is like if we had one word to describe the weather. Would you say, is it hot or cold? Or is it dry or wet? Is it light or dark? How much more detail could we have if we could have 2 digits per sample to describe things? Well, we quadruple the amount of values that we can have here. Just like if we could use 2 words to describe the weather, we could say very hot and moderately hot, very cold and moderately cold. And you can see we get a higher resolution vertically each time we go up in bit depth. For CD quality, and for many streams, 16 bits is standard. Many high-quality systems use 24 bits, and that's plenty of dynamic range, more than we can hear. But here, if we have 16 bits per sample, it'll sound like our ordinary sine wave. And if we cut that a little bit, we're not really going to notice. But listen, as some artifacts start to creep in. You can see them a little bit, you can start to hear them. It's not a pure sine wave anymore. We're getting some extra junk in there. You can start to see them appearing. They're not evenly spaced. So this sounds a lot louder because it's spending more time away from zero, and it's also getting brighter because we're getting higher frequency artifacts introduced.